Welcome to the Padhai Kar Lo JEE preparation channel. You can practice more problems on this exact topic on our Padhai Kar Lo Android app, link in the description below, or on our website padhaikarlo.com. Today's chapter is chemical bonding and molecular structure, arguably the single most conceptually foundational chapter in all of JEE inorganic and physical chemistry, since bonding ideas resurface constantly, inorganic mechanisms, coordination chemistry and periodic trends. In this video we'll cover ionic and covalent bonding basics, VSEPR theory and molecular shapes, hybridization, molecular orbital theory, bond parameters and hydrogen bonding with resonance. Let's begin. Ionic bonding forms through the complete, essentially total transfer of one or more electrons from a metal atom to a non-metal atom, producing oppositely charged ions that are then held together purely by strong electrostatic attraction, and this specific bond type is favored when the difference in electronegativity between the two combining atoms is genuinely large. The overall favorability of forming a specific ionic compound is best understood through the Born-Haber cycle, which combines several distinct energy terms: sublimation energy of the metal, ionization enthalpy to actually form the cation, dissociation energy of the non-metal, electron gain enthalpy to form the anion, and finally lattice energy, the energy released when the gaseous ions come together to form the solid ionic lattice. And it's specifically this final lattice energy term that's overwhelmingly the largest contributor, making ionic compound formation genuinely favorable overall. Lattice energy itself depends on two key factors. It increases with increasing ionic charge, since electrostatic attraction is directly proportional to the product of the charges, and it increases as ionic radius decreases, since smaller ions can approach closer together, increasing attraction. This is precisely why magnesium oxide, with +2 and -2 charges, has dramatically higher lattice energy, and correspondingly a much higher melting point than sodium chloride, with only +1 and -1 charges. Fayon's rules further describe when a formally ionic bond actually develops significant covalent character. This happens with small highly charged cations and large, easily polarizable anions, since the cation's concentrated positive charge distorts, polarizes the anion's electron cloud, pulling shared electron density back toward itself. Covalent bonding forms through genuine mutual sharing of electron pairs between atoms, typically between two nonmetals with comparable electronegativity, and Lewis structures represent this sharing by drawing bonding pairs as lines, and non-bonding lone pairs as dots, with every atom, other than hydrogen, and a handful of specific exceptions, generally aiming to achieve a full octet of 8 surrounding electrons. When multiple valid Lewis structures can genuinely be drawn for a single molecule or ion, formal charge calculation helps identify the actual most accurate, most representative structure. Formal charge equals the number of valence electrons an atom would normally have on its own, minus non-bonding electrons it actually keeps, minus half of all its bonding electrons, and the structure where formal charges are closest to zero overall, and where any necessary negative formal charge sits specifically on the more electronegative atom, is genuinely the most stable, most accurate representation. Certain molecules genuinely violate the standard octet rule in 3 specific, well-defined ways. Incomplete octets occur in electron-deficient compounds like boron trifluoride, where boron has only 6 surrounding electrons. Expanded octets occur in elements from period 3 onward, like phosphorus pentachloride and sulfur hexafluoride, which can accommodate more than 8 electrons by using available MTD orbitals, and odd electron species, like nitric oxide, simply cannot satisfy the octet rule for every atom, since they contain a genuinely odd total number of valence electrons. Valence shale electron pair repulsion theory, VSEPR, predicts a molecule's actual three-dimensional shape based on one simple core idea: electron pairs around a central atom, whether their bonding pairs or lone pairs arrange themselves in space to be as far apart from each other as geometrically possible, minimizing mutual electrostatic repulsion. The specific electron pair geometry depends directly on the total number of electron domain around the central atom. 2 domain gives linear geometry, 3 gives trigonal planar, 4 gives tetrahedral, 5 gives trigonal bipyramidal, and 6 gives octahedral, but the molecular shape, which is what's actually reported as the final answer, only counts the positions of atoms, not lone pairs. So a molecule with 4 total electron domain but only 3 of them being actual bonding pairs like ammonia, is still tetrahedral in its underlying electron geometry, but described specifically as trigonal pyramidal in molecular shape. Crucially, lone pairs occupy demonstrably more space than bonding pairs do, since they're held closer to just the one central atom's nucleus, and aren't stretched between two nuclei. This means lone pair to lone pair repulsion is strongest, lone pair to bonding pair repulsion is intermediate, and bonding pair to bonding pair repulsion is weakest. And this specific repulsion hierarchy is exactly why water's bond angle, one oxygen with 2 lone pairs, compresses to about 104.5 degrees, notably less than methane's perfect 109.5 degree tetrahedral angle, with 0 lone pairs, and ammonia's angle, with just 1 lone pair, sits at an intermediate 107 degrees. Hybridization is the specific process of mixing atomic orbitals of comparable energy on a single atom to form new, equivalent hybrid orbitals better suited for the actual geometric bonding pattern observed. sp hybridization mixes one s and one p orbital, producing 2 hybrid orbitals arranged linearly at 180 degrees, seen in beryllium chloride and in carbon atoms involved in triple bonds. sp2 hybridization mixes one s and 2p orbitals, producing 3 hybrid orbitals arranged trigonally at 120 degrees, seen in boron trifluoride and in carbon atoms involved in double bonds. sp3 hybridization mixes 1s and 3p orbitals, producing 4 hybrid orbitals arranged tetrahedrally at 109.5 degrees, seen in methane and in every carbon atom involved purely single bonds. A genuinely important fully tested connection: the number of hybrid orbitals a central atom uses always exactly equals its total number of VSEPR electron domain sigma bonds plus lone pairs, so you can actually determine hybridization directly and reliably from VSEPR geometry, without needing any separate, independent calculation. It's also worth remembering explicitly that hybridization specifically describes only sigma bond framework and lone pair orbitals, pi bonds, formed by unhybridized, genuinely leftover p orbitals overlapping sideways, are entirely separate from this hybridization scheme, which is exactly why a carbon atom can be sp2 hybridized while still participating in one additional pi bond, forming its overall carbon-carbon double bond. Molecular orbital theory offers a genuinely more complete, quantum mechanically rigorous picture of bonding than the simpler valence bond and VSEPR approaches. Atomic orbitals from different atoms combine mathematically to form entirely new molecular orbitals that belong to the whole molecule collectively, not to any single atom individually. When 2 atomic orbitals combine, they produce one bonding molecular orbital lower in energy, where electron density is genuinely concentrated between the 2 nuclei, reinforcing attraction, and one antibonding molecular orbital higher in energy, marked with an asterisk, where there's specifically a node, a region of 0 electron density directly between the nuclei, actually weakening the bond. Bond order is calculated as 1/2 times the quantity, number of electrons, in bonding orbitals minus number of electrons in antibonding orbitals, and it directly, quantitatively predicts both bond strength and bond length. Higher bond order genuinely means a stronger shorter bond. Molecular orbital theory succeeds specifically where simpler valence bond theory clearly fails. It correctly, directly predicts that molecular oxygen is paramagnetic, genuinely attracted into a magnetic field due to unpaired electrons sitting in degenerate p antibonding orbitals, a well-established experimental fact that simple Lewis dot structures, showing all paired electrons, cannot explain at all. It also correctly explains why helium molecule, He2, simply does not exist, since it would have equal numbers of bonding and antibonding electrons, giving a net bond order of exactly 0, and therefore genuinely no actual stabilizing bond whatsoever. Bond length, the equilibrium distance between 2 bonded nuclei, decreases as bond order increases. A carbon-carbon single bond is longer than a double bond, which is longer still than a triple bond, since increasing shared electron density pulls the 2 nuclei progressively closer together. Bond length also decreases as the atoms involved get smaller. Moving across a period or up a group generally shortens bond length due to decreasing atomic radius. Bond dissociation energy, or bond enthalpy, the energy required to actually break 1 mole of a specific bond in the gas phase correspondingly increases as bond order increases. Triple bonds are the strongest, requiring the most energy to break, though they are, notably, not simply 3 times a single bond's strength, since pi bonds are generally somewhat weaker than sigma bonds due to less effective sideways orbital overlap compared to direct head-on sigma overlap. Bond angle is determined primarily by hybridization and specific lone pair repulsions, as already established, but it's also measurably affected by the relative electronegativity of surrounding substituent atoms. More electronegative substituent atoms pull shared bonding electron density away from the central atom, which reduces electron-electron repulsion specifically between those particular bonding pairs, allowing the overall bond angle to close in slightly. This is precisely why the bond angle in phosphorus trifluoride is measurably smaller than in phosphorus trihydride, despite both molecules sharing the exact same underlying sp3 hybridization, an identical VSEPR electron domain count. Resonance occurs when a single molecule or ion genuinely cannot be accurately represented by just one single Lewis structure, and its actual electronic structure is instead better described as an average, a hybrid or 2 or more valid contributing resonance structures. The classic example is the carbonate ion, where the negative charge and double bond character are, in reality, genuinely delocalized equally across all 3 oxygen atoms, rather than being fixed rigidly on just one. This real delocalization is exactly why all 3 measured carbon-oxygen bond lengths in the carbonate ion are experimentally found to be identical, and intermediate in actual length, between a typical single and typical double bond. Resonance structures are not different molecules rapidly interconverting back and forth, they are simply alternative ways of drawing one single, unchanging, actual structure, and increasing genuine resonance. Delocalization generally increases a molecule's overall thermodynamic stability. Hydrogen bonding is a notably strong specific type of intermolecular attraction, distinctly stronger than typical van der Waals forces but still clearly weaker than an actual covalent or ionic bond, occurring specifically when hydrogen is directly covalently bonded to a small highly electronegative atom, nitrogen, oxygen or fluorine, and that same hydrogen atom is then also separately, additionally attracted to a lone pair on a nearby electronegative atom on a different, neighboring molecule. Hydrogen bonding is precisely why water has such an unusually, anomalously high boiling point compared to other similarly sized molecules, and it's also the exact structural principle holding DNA's 2 complementary strands together in their characteristic double helix. For any JEE bonding question, follow a consistent reliable sequence. First, draw the correct Lewis structure, counting total valence electrons carefully, and check for any octet exceptions, incomplete, expanded or odd electron, before assuming a standard structure applies. Second, count total electron domain around the central atom, to determine both the underlying VSEPR electron geometry, and the corresponding hybridization, remembering that domain count and hybridization are always directly, reliably linked together. Third, determine the actual final molecular shape specifically by considering how many of those domain are genuine bonding pairs versus lone pairs, and adjust your expected bond angles slightly downward from the ideal, unperturbed value to account for the specific repulsion hierarchy, lone pair repulsion being strongest. Fourth, for any molecular orbital theory questions, carefully fill electrons into molecular orbitals following the correct standard energy level ordering for that particular row of the periodic table, remembering that this specific ordering genuinely differs slightly between elements before and after nitrogen due to sp orbital mixing effects. Before calculating final bond order, a commonly tested trap worth flagging explicitly: don't automatically confuse molecular polarity with individual bond polarity. Molecule can easily contain individually polar bonds yet still be overall nonpolar as a whole, if its molecular geometry is sufficiently symmetric that all those individual bond dipole vectors cancel out completely. Carbon dioxide with 2 identical, oppositely directed polar bonds, in a perfectly linear arrangement, is the single most classic example of this exact distinction. Dipole moment is the specific quantitative measure of a bond's or a molecule's overall polarity. defined as the product of the magnitude of separated charge and the distance between the centers of positive and negative charge, and it's conventionally represented as a vector arrow pointing from the positive end toward the negative end or that separation. For a diatomic molecule, dipole moment depends directly and simply on the electronegativity difference between the two bonded atoms. A larger difference produces a genuinely larger bond dipole. For polyatomic molecules, the overall net molecular dipole moment is found by taking the complete vector sum of every individual bond dipole present, which is precisely why molecular geometry matters so critically for determining overall polarity. Carbon dioxide has two identical, individually polar carbon-oxygen bonds, but its perfectly linear geometry means those two bond dipole vectors point in exactly opposite directions and cancel completely, giving a net molecular dipole moment of exactly zero, making carbon dioxide an overall nonpolar molecule despite containing genuinely polar individual bonds. Water, by clear contrast, has a bent nonlinear molecular geometry specifically due to its two lone pairs, so its two individual bond dipoles do not cancel, they add together vectorially, giving water a substantial net dipole moment, and this is exactly why comparing the dipole moments of boron trifluoride, trigonal, planar and nonpolar overall against ammonia, trigonal pyramidal and clearly polar overall, despite both technically having three identical bonded atoms around a similarly sized central atom, is such a genuinely favorite, frequently recurring JEE conceptual question. Let's recap this entire chapter. Ionic bonding is driven by lattice energy, favored by high charge and small radius, while covalent bonding follows Lewis structures and the octet rule, with formal charge picking the best structure among alternatives. VSEPR predicts molecular shape from electron domain repulsion with lone pairs compassing bond angles, and hybridization, sp2 sp3, always matches the total domain count. Molecular orbital theory correctly explains oxygen's paramagnetism and predicts bond order directly, while bond length and energy both track bond order closely. Resonance describes real electron delocalization across multiple contributing structures, and hydrogen bonding between H and NO, or F, explains water's anomalous properties and DNA's double helix structure. That's the complete chemical bonding and molecular structure chapter for JEE. Keep the VSEPR to hybridization link and the molecular orbital bond order formula sharp. They're used constantly across the rest of your chemistry syllabus. If this video helped, please like it and subscribe to Padhai Karlo for more JEE preparation content just like this. See you in the next one.